think I will just start. Yeah, so first let us just fix this gloss gadget thing. So, what did I have yesterday? That yeah. Okay, and the external edges are what we had earlier. Okay, so these are the external edges. So, once again let us see that why this should work. So, suppose if none of the external edges are taken, then we have the cycle cover basically by taking this pair and this pair of edges, right. So, this is for none of the things. Suppose if we only include the bottom edge, so then the cycle cover is so we have this, and then these two, right. So, this is the first cover which has no external edges, okay, and this is the second cycle cover which has exactly this external edge. So, this is the second one. The third one is suppose if I have to include this one, so then I have this edge and this. For the fourth case, we have this basically by symmetry. Fifth one is suppose I have these two, then I take this as my cover, and the last one is we have this and this. So, now we go this way, and the seventh one is just symmetric to the sixth one. Okay. So, just leave it. And these are the only 7 cycle covers in this graph corresponding to these set of things. Okay, so let us come back to interactive proofs. So, we saw this class IPK yesterday. So, basically the model is so there is some prover, okay, and there is a verifier. So, given an input x, both has access to this input. So, what the verifier does is the verifier computes the string A1, which is V of x, and also we allow the verifier to be probabilistic. So, it can toss coins. So, we just denote that by some random string r. Okay. So, r is a string in chosen randomly from of length, let us say some m. Okay. So, this guy sends its message to the prover. Now, what the prover does is it computes A2, which is P of x comma A1, and sends it to the verifier. The verifier computes A3 depending on what x, r, A1 and A2 is, sends it to the prover, and so on. Finally, the prover, let us say, sends some answer AK, and based on that the verifier decides whether it would accept or reject the input x. Okay. So, this is essentially what the model is. And what do we have, that if x does belong to the language. So, we want to decide if a particular language, I mean if x belongs to a language or not. So, then the guarantee that we have is that so there exists a prover such that for at least two-third fraction of the r's, we will accept. Okay. And if x does not belong to L, then no matter what the prover function is, for at most 1/3 fraction of the r's, the verifier will be able to accept. So, this is what the model was, and we said that we will denote this class IP to be IP with polynomially many rounds. Of course, I mean it does have a hierarchy. The question is whether it is a proper hierarchy, right. I mean of course, IPK defines a certain class of language and IPK plus 1 defines another class, but what is the relation? So, we will talk about that. So, actually if k is constant, if k does not depend on the size of the input, then what we can show is that everything collapses to IP2. Okay. So, it is just basically a the verifier asking one question and the prover answering back, and based on that the verifier can decide whether to accept or not. Huh? Or I mean it depends. No, see basically the way you can think of this is maybe to compute the first question, the verifier uses, let us say, the first few random bits, let us say the first 5 random bits of r, and then to compute A3 he uses the next 10 whatever. So, ultimately the total size is some polynomial. So, we can always assume that it is the same r that the verifier has access to. Okay. Which one? M. Yeah, I mean. So, whenever we talk about an IPK, we are fixing k. So, we want the number of rounds to be bounded by some k. So, yeah. So, the crucial point here is that the prover does not have access to R. In other words, whatever the coin tosses that is being conducted by the verifier, that remains hidden from the prover. Okay. So, we will soon see why it is so important. So, let us look at an example. So, consider the following language, the language of graph non-isomorphism. So, you are given two graphs G1 and G2 as your input, and you accept this if G1 is, so this is the sign for not isomorphic, to G2. Okay. So, third year guys, you saw this question in your 340 course, that the graph isomorphism problem is in NP. Okay. And that is not very difficult to show, because the way you argue it is in NP is you just guess a permutation. Okay. So, if G2 is that permutation operated on G1, then of course, you accept, otherwise not. So, if the graphs are isomorphic, there exists some permutation, otherwise there does not exist. So, that immediately implies that graph non-isomorphism is in co-NP. Okay. So, can we say something more? So, can we give a interactive proof model for graph non-isomorphism? So, as it turns out, what we can show is that graph non-isomorphism is in IP2. So, in 2 rounds of an interactive proof, you can decide graph non-isomorphism. And the algorithm is quite simple as well as the analysis. So, the algorithm is that given G1 and G2, what the verifier does first is it tosses a coin, okay, and depending on whether it is head or tail, it chooses an I from the set 1, 2. So, pick I randomly from 1, 2. Okay. And then permute the vertices of G I again randomly to get, let us say, a graph H. Okay. So, what the verifier does is it tosses a coin. Suppose if it is head, it will choose I to be 1, and if it is tail, it will choose I to be 2, and then depending on what I is, it will permute the vertices of G I. So, if it comes out head, it will permute the vertices of G1, otherwise it will permute the vertices of G2 to get a graph H. Okay. So, clearly H is isomorphic to Gi, since it is just permuting the labels of the vertices of Gi, and then it sends H to the prover. So, what the prover does given H is, so prover has infinite computational power. So, what he does is he checks if H is isomorphic to G1 or G2, okay, and sends J such that H is H is isomorphic, he sends J such that H is isomorphic to G J to the verifier. And now what the verifier does is, if I is equal to J, then we will accept, else we will reject. Okay. So, that is the complete protocol. So, now let us see that suppose if we have a graph G1 and G2 which are not isomorphic. So, if G1 is not isomorphic to G2, what happens? What can we say? So, if G1 is isomorphic to G2, then with probability 1, we will accept, right, because the graphs are not isomorphic. So, there is no way in which I mean the prover can always find that out, but the problem is if the graphs were isomorphic. So, if G1 let us say is isomorphic to G2, then what happens? So, then in this case H is isomorphic to both G1 and G2, and the prover finds that out that H is isomorphic to G1 and G2, and then he just sends back some J. So, so the probability that J will be equal to I is exactly half, right. So, if G1 is isomorphic to G2, then with probability half, J is not equal to I. Okay. But now what we can do is, if you want, because we want to boost this probability, we can take repeated trials. I mean what the verifier does is it finishes one round, so then it again does the same thing. So, then it again computes a random I mean again it does a random coin toss to get an I, it generates a graph H, and it again asks the prover which of the two graphs is this isomorphic to, and depending on the answer it again outputs. Okay. So, if at even in one of the cases the verifier gets that I is not equal to J, then he knows that the graphs have to be isomorphic because the prover has been fooled. Okay. So, let us say he takes t trials, the probability that in none of the t trials the prover will be fooled is 1 over 2 to the power t. So, the probability that in at least one of the t trials the verifier gets the correct answer is 1 minus 1 over 2 to the power t. So, that is sufficiently high probability. Yes.
But is also sending 1 or 2 that is randomly if both of them are isomorphic.
I mean you can say that if both of them are isomorphic, he will always send 1, you can just fix that, does not matter, because he does not have any choice. I mean he cannot make out which graph the verifier had permuted to generate H. So, might as well we can just send it. So, we assume that the prover is a deterministic machine. So, we will always assume that he sends 1 in that case, does not matter.
Also, verifier can send it in the first place.
Huh? Verifier?
Can send it in the first place instead of H.
Verifier can send what?
Any of the graph, I mean without permitting.
No, I mean the graphs are always I mean the prover has access to both the graphs. So, that is the point. So, now the goal, so what is the goal of the prover? So, again here we are assuming that let us say that I am the verifier and you are the prover. So, you want to convince me that these two graphs are not isomorphic. Okay. So, suppose even if the input is that the two graphs are isomorphic, you can always tell me that no, these two graphs are not isomorphic, and I have no way to find that out because my computational powers are limited. Okay. So, I am handicapped as far as computational powers are concerned. So, I cannot find that out.
So, what is this permitting?
Which one? because he wants to hide the fact from the prover that which of the graphs is H isomorphic to. Okay. So, let me just pose the question in a different way. So, what you are asking, let me just pose it in a different way. What if the prover had access to this coin toss? In other words, what if the prover could see what is the result of the coin toss? In that case, he can easily fool the verifier. I mean, if the verifier, let us say, comes up with 1, then the prover knows that okay, this guy is going to permute the vertices of G1 to construct 8. So, I might as well output J is equal to 1. Okay. And if he gets the thing as tail, just the other way around. So, here it is very, very important that this coin toss is a private coin toss. I mean, the prover does not have access to whatever is the random bit that the verifier is using, because otherwise he can fool the verifier. Huh? Yes. So, again if he knows this random string, then he can just compute the inverse of that permutation and get back the original graph and then find out which of the graph he had permuted. Okay. Because the prover's goal is always to accept whatever the input is. Okay. He does not care, but the verifier is skeptical. The verifier will not allow a wrong input to get accepted.
In case we are using multiple tries, so we are sending all the permuted graphs at the same time, or we are sending it same.
You can send it at the same time also, does not matter. So, you can let us say take you can make t coin tosses here, you can generate H1 to Ht, send them all to the prover, and but now some of the graphs will be, some of the Hi's will be isomorphic to G1 and some of them will be isomorphic to G2. Okay. The verifier knows which is isomorphic to what, because he had tossed the coins. So, he has all that information. So, now depending on what the answers, yeah, so he can send a vector of values, but he cannot send his random bits, he can only send these graphs that he is constructing. And then depending on what the prover is doing for each of those graphs, the verifier will finally be convinced with very large certainty. Okay. So, again, so the point is that how these coin tosses are being conducted, I mean whatever is the random string that the verifier uses, is it a public random string or a private random string, does make a significant difference. So, is this clear to everybody, this protocol and the idea behind it? Any questions? So, IP1, so IP1 means that the prover cannot say, so it will be BPP, I would guess, because what does IP1 means? IP1 means that the verifier is just sending a string, but it cannot get any answer back from the prover. Okay. So, if he is just sending a string, it is same as doing nothing. So, it is just a probabilistic machine sitting over here. So, it is the same as BPP. Okay.
Send the original graph.
Okay.
Then also it is outputting the first one.
Okay.
So then also it can, that is also a correct algorithm.
So, if it does not permute at all, so if it just sends yeah. So yeah, so the goal of the prover is to make the verifier always accept. So, he will just check that which of the two graphs this is equal to. So, if the verifier had sent G1, the prover will just send 1 back to the verifier, and if the verifier had sent G2, then the prover will just send 2 back. So, it always, the verifier always ends up accepting. Yeah, Oracle is always supposed to return the correct. So, Oracle is totally different. Oracle is in terms of a language. Okay, so there is some language which is your Oracle, and you are just asking whether a string belongs to that language. Okay, so the Oracle does not have any hidden motive to make the fine. Oracle is a black box, but it does not have any hidden motive. So, here the motive of the prover is to always make the verifier accept no matter what the input is. Okay. And the goal of the verifier is to be skeptical and only accept those things which are in the language. But Oracle does not operate with any such agenda. So, so as somebody said that it always gives the correct answer. SAT bar is CoNP complete. So, so CoNP is not known to be in IP2. I mean, in the sense that I think if CoNP is shown to be in IP2, then the polynomial hierarchy will collapse. So, we will see that. So, we will see more results about these classes in the coming few lectures, but it is very important that the model is clear to everybody as to what we are dealing with here. Okay. So, now that we saw this thing about private coin tosses, let us ask the question that what happens if the random variables are accessible to the prover as well. Okay. So, so we define the class AM. So, AM stands for Arthur Merlin. So, AMK is the class of all languages that belong to IPK. So, it is a subset of IPK such that the prover has access to every random bit that the verifier uses to compute its message. Okay. So, there is this subtle point here. The point is that here we had assumed that the entire random string is available to the verifier, but the point is that, so see the way I phrased this definition, the prover has access to every random bit that the verifier uses to compute its message. Okay. So, when it is computing the message A1, whatever are the random bits that the verifier uses to compute A1, the prover has access to only those random bits and not the rest of R. Okay. So, again in the next round, again when it is computing A3, let us say it uses some other set of random bits, again the prover will know what those random bits are. Okay. So, in other words, there is no screen between the prover and the verifier in this case. So, whatever are the coin tosses that the prover, I mean the verifier makes, the prover can see the answer to those coins. Yes, he can remember. So, both of them can remember early coin tosses, because they are I mean the prover has unlimited computational power. So, he can remember anything and do anything. Even the verifier can remember earlier coin tosses because it is a polynomial time machine. So, he can store those bits in some tape. Okay. But the point is that now this kind of a thing cannot happen. I mean I cannot say that graph non-isomorphism is in AM2. Okay. But as it turns out that is also true, but by a totally different argument, and we will see that probably on Friday that graph non-isomorphism can also be shown to be in AM2. Okay.
So here the prover will not know this one or which out of one or two is come, but it will know that which out of one or two is come, but it will not know which permutation.
You mean in the R-thermal?
Machine like
You mean in this protocol?
Because there are only two messages. Even though they share which is sent.
it will not know what permutation it is. It will also know what permutation it is put onto G one or two.
In this model it does not know, here it does not know, here basically everything is hidden from the prover. Okay. Whatever V is doing, he is doing it secretly.
So if in AM like that AM type,
Yeah.
so here it will know which out of one.
Yes, in AM it will know. I mean if this were to be an AM model, then
Also know what
yes, what is the permutation? Exactly. Yeah. So that is why we need a completely different protocol to be able to show that graph non-isomorphism is in AM2. This will not work. So that we will see next class. But yeah, so this is the basically the difference is what is known as public coin protocol versus private coin. Okay. So, in one case the prover has access to the random bits of the verifier, and in the other case it does not. So, let us look at some properties of this these classes. Some of them are easy to see, but others we will prove later on. So, of course, by definition AMK is contained in IPK. Okay. What is also known, and this is more non-trivial, is that AM k plus 1 is contained in AMK for k greater than or equal to 2. Okay. So, any Arthur Merlin model, okay, with some constant rounds of interactions can be brought down to 2 rounds of interaction without any loss of generality. Okay. So, this is more non-trivial. So, you can try this out, but let us see, we will probably discuss a proof of this maybe after the. So, yeah, so this always is the number of rounds. So, how did I define a round? So, a round is a message, right? Huh? Doesn't matter actually. Yeah. So, therefore, this class AM, so this is more of, so I should not state this as a property, but this is a convention So, whenever we say AM, so this refers to AM2. Okay. So, the verifier makes some coin tosses, sends a query to the prover. The prover does some computation, sends back its answer to the verifier, and then again it does some probabilistic computation, and depending on what that answer is, it either accepts or rejects. So, that is what the language AM is. Yes. Basically for okay, not for this reason, but so it's because of this property. So, the third property about these classes is that so AMK is contained in IPK by definition. IPK is contained in AMK plus 2. Okay. And this is again something non-trivial, and we will look at a proof of this later on. So, because of this, again any constant labels of the IP, I mean any constant rounds of the IP protocol can be brought down to 2 rounds. Okay. Okay, and this maybe you can try. So, what again is known as AM is equal to this class BP dot NP. Okay. So, this I will leave as an exercise. So, recall what the definition of this class was. So, it is a BP operator prefixed to this complexity class NP. So, this just try as an exercise. So, let me mention this. So, why was this term Arthur Merlin coined for this class? So, again that is because of some historical region. So, in medieval times in England there was some king called Arthur, and he had a court magician by the name of Merlin. Okay. So, the idea here is that the king will ask Merlin some questions, and Merlin is always able to give the correct answer no matter what the king asks, and whatever coin tosses that the king makes. So, they are also not hidden from Merlin. Okay. So, when this class was first introduced, so this was in 87 by Lacy Babai. So, he had that model in mind, and that is why he gave this name. Okay. So, what if we just change the protocol a little bit, and instead of Arthur first asking the question, what if Merlin decides to send some string to Arthur first, okay, and then depending on that Arthur would accept or reject. So, that is what this class MA is, which is Merlin Arthur. So, Merlin Arthur is so how do we define this? So, one way to define this is using the interaction model, but there is also another way to define it. Let me use that. So, L is said to be in this class MA if there exists a probabilistic polynomial time machine V such that for all x belongs to L implies that there exists some certificate y, basically the certificate that Merlin sends to Arthur, such that with high probability Arthur would accept. So, that is with probability z V given x y and z. Okay, so this is a probabilistic machine, so I might not as well include this. So, V given x comma y accepts is 1/3. Huh? No, I mean again I mean so yeah, so here we just have 2 rounds, so just or maybe just 1 round, because Merlin sends a string to Arthur and then Arthur decides to accept or reject. So, MA k would probably be contained in AM k plus 1 or something like that. So, for exactly. So, if you look at this definition of MA, it is the same as that of NP, but the verifier is a probabilistic machine. Okay. And actually it is a conjecture. So, this is a very widely believed conjecture in complexity that MA is probably same as this NP. So, again BPP is contained in MA, right, because given an X, if it just does not use the answer that Merlin sends Arthur, so without using Y, this machine is just a BPP machine. Okay. So, by definition MA contains NP as well as BPP, but it is also conjectured that these two classes are the same. Which one? NP dot BP does not make sense, no, I mean what do you mean? BP dot NP is separate, because BP dot NP is again seemingly more powerful, because what is happening in AM2 is first the verifier does something, then it asks a question, and then depending on the answer it decides to accept or reject. But here this is I mean this clearly has lesser power, because this this Y does not depend on a question that the verifier asks. This is just some string which Merlin decides to send to Arthur. Verifier is always probabilistic. So, we are always dealing with So, what is NP dot BPP? How do you define that class?
BPP dot something.
So, BP dot C was there exists dot BPP.
That is not true, because for all y there might be some strings, but their probability is less.
Yeah, but that is why you are using the fact that it is a BPP machine. So, what is there exist dot C? So, if x belongs to L, then there exists a y such that this is a should be, I mean I do not see anything wrong in that. Maybe you can call it as there exists dot BPP. You mean if this is true? Yeah, if this is true, then yes. If that is closed under polynomial probabilistic polynomial reduction, then does it imply this? That I do not think that maybe, but that is more difficult. I do not see how that gets implied. Yes. It does, because he has access to x. So, depending on what x is, he is sending a string y. So, he does have, but the question is that his y is not an answer to some question which the verifier asks. It is basically like a certificate. Okay, so we will stop here.